Check, check, test, test. Doing a little mic check. We're going to start in about a minute. Hope you guys can see and hear me. Feel free to enter something in the chat indicating that you can and do, and I'll be right with you. There's our fancy new building. If you haven't seen it yet, this is not live. I recorded this about 6 months ago, but there you go. That's where we're coming to you live from today. We'll start very soon. Hey everybody, welcome to the big show, the live show from the live, glorious new Goldendale Observatory State Park. I wish you guys were here in person, but we're doing this via telecom in the meantime. Speaking of telecom, the topic of tonight's show is telecommunications technology, specifically satellites. You might see some objects whizzing around my head in the background. Those are actually satellites. This is a simulation depicting satellites orbiting Earth as viewed from this location. This is not real. I've sped it up quite a bit so you can appreciate the motion of the satellites a bit more. But we will be talking about these robots, which do indeed surround our planet. On that subject, let's get right down to it. This is a live chat, live show for a reason. We want you guys to interact with us. One of the cool things about Goldendale Observatory is we don't just give one-directional presentations. We don't just lecture endlessly. We very strongly believe in Socratic method. This is a conversational teaching style. So please interact, ask questions. And I'm very pleased to announce this is the first episode of Goldendale Observations coming to you via the YouTube Live platform. And I was not paid by Google to say this, but I have to tell you I like YouTube Live. The quality is very good, or at least I hope it is. I hope you're seeing a good quality feed. I am seeing a good quality return here. And importantly, the latency is very low. That is the delay, the transmission delay, how long it takes the, in this case, video to get out to the servers and then come back. Theoretically, we should have less than a 4-second round trip. So that means that I can hopefully ask for questions and you will hopefully provide some. During the chat, I'm encouraging some volunteers to copy the best of, so to speak, the greatest hits of the chat log, and I will hopefully be able to answer all those questions during the 1 hour that I have with you tonight. Speaking of 1 hour, it might go a little short, it might go a little long, but we're gonna shoot for about 1 hour of time. Those of you who have never been to Goldendale Observatory, it is a public educational facility. We hope that by the end of this show, you will know more than you did at the beginning of the show. And one of the ways we can ensure that is, again, you asking questions. All right, so we're going to talk about satellites, like I said, and this is not new information. Earth has been surrounded by satellites since when? Really the 1960s. The 60s is where various companies and countries realized that the future was space. But the story starts a little bit earlier, way back in the year 1957. This was the International Geophysical Year, and during this time, various world governments decided it would be a good idea if we addressed the problem of hostility. The various countries of the world had been at war with each other. There was all sorts of paranoia associated with that hostility, and people realized that, especially scientists, realized that scientific study was being curtailed, and we were spending huge amounts of time and money on things other than research. So during the International Geophysical Year, there were 11 line items, 11 Earth sciences identified that were expected to bring an opportunity for collaboration between nations. There were actually 67 signatory countries. And not only was it an opportunity for everybody to work together and be friends, it was also an opportunity to solve some old mysteries. By the mid-20th century, technology had evolved to such an extent that we could start to really crack these old nuts. And some of the most important discoveries of the 20th century began around this time during the International Geophysical Year. So some of the earth sciences that were addressed included aurora, the northern and southern lights, air glow, which is the green glow caused by chemical reactions in the upper atmosphere, cosmic ray impacts, the Earth's magnetic field, Earth's gravity, ionosphere. We wanted to know more about that mysterious upper layer of Earth's atmosphere. Also, it was a time where precision mapping was prioritized. We started to really nail down the latitudes and longitudes of our planet, which would end up being very important and support a lot of future studies. We also embarked on new meteorological studies. Expeditions were sent all over the globe, including famously some to the Arctic and Antarctic. Also oceanography, same story. Ships all over the planet going all different places. Seismology and volcanism, and then something that applies a lot to what we're going to talk about tonight, solar activity. The sun was unusually active during the International Geophysical Year, and it made it a good time to study it. All that being said, of all the items I just listed, the one let's say experiment or achievement that really steals the show is this thing. So what is that? I'm not going to tell you. I'm hoping at least some of you know. So I'm going to wait. I'm going to watch the chat. Somebody tell me what you're looking at there. What is that thing? I'm watching the chat. I'm going to be real sad if no one says it. Oh, yeah. Oh, well, that was pretty close. So someone spelled it with a C. It's a K. Sputnik. There you go. I don't know if it's Sputnik or Sputnik, but it's the Russian word for satellite, which is also the Russian word apparently for a traveling companion. So it's kind of a poetic term. And the word satellite in English or Russian doesn't actually specifically imply a robot. Natural satellites have, of course, existed for billions of years, and the term satellite used to apply to natural bodies, like, for example, moons. So tonight we're not talking just about satellites, we're talking about artificial satellites. Although in modern parlance that term has come to encompass mostly just artificial satellites. That's usually what people are talking about when they say the word satellite. So why did I bring up Sputnik? What's the big deal with Sputnik? It was the first successful orbital device. Sputnik was the first successful satellite. It actually did go into orbit and stay in orbit for about 3 months and didn't come crashing back to Earth. There had been launches before, which entailed a ballistic trajectory where an object went up into space, but then didn't fall into orbit. It just came back to Earth and either burned up or crashed into the ground. So Sputnik didn't do that. Sputnik actually did orbit the Earth. It was a big deal. Sputnik didn't have much to it. It wasn't really a science instrument. It literally was a container with a battery in it and a radio transmitter. You see those antennas, and all it did is go ping, 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 set out radio pulses, which allowed people all over the world to observe its presence, confirming that it did indeed exist. Sputnik was not that big. A lot of people don't realize it's about the size of a beach ball there. See, this is a technician working on Sputnik before its launch. You'll find a lot of the early satellites were not very big. And there's a very good reason for that. Heavy objects are difficult to get into space because the heavier the payload, the more fuel you need. Now, when we look at, for example, hold that thought. When we look at rockets, they are essentially a stack of fuel. So this is a multi-stage rocket. This was actually used to launch a satellite we'll be talking about in a few minutes. This pile of fuel is really just there to accelerate the rest of the assembly through Earth's atmosphere, to break the surly bonds of Earth, as they say poetically, to blast its way through Earth's atmosphere, which produces very serious drag at high velocities, and get the rest of the assembly up high enough and fast enough so that it can take over and either fall into orbit immediately or fire a second stage, which will put the payload into orbit. The heavier the payload, again, the more fuel you need to propel it. But here's the problem. Fuel is not weightless. The fuel has mass. So you must add more fuel to your rocket to propel the fuel, which you added to propel the payload. But now you've added more fuel. So now you have to add even more fuel to propel the fuel that you added to propel your payload. This is the tyranny of rocketry. Rocket science is very unforgiving in this way. Your fuel requirements do not increase linearly. They increase exponentially with payload increase. And so early satellites, again, were quite lightweight. So, back to Sputnik. Not a very big satellite. A great triumph for the Soviet Union. They immediately followed up with Sputnik 2. And then the Americans got in on the show, and they launched this thing. This is Explorer 1, the first successful American satellite. Notice it looks like a missile. That's because it is a missile that was repurposed as a satellite. Again, notice it's not very big, and notice it's light enough that these three gentlemen can lift it. And by the way, these are not three random gentlemen. The guy on the left you may not be aware of. That's William Pickering, Dr. William Pickering. However, the other two guys you might be aware of. So this one in the middle, that is Dr. James Van Allen. And there's a very famous series of belts named after him. That's very appropriate. Hold that thought. And then arguably a much more famous guy, Wernher von Braun, the great German rocket man who came to the United States after World War II and helped us leave this planet. He looks pretty young in this picture. This was taken in 58, yes. Mr. Van Allen there in the middle became famous for his Van Allen belts, the radiation zones above Earth's surface, caused by our own magnetic field trapping energetic particles from the sun, along with high-energy electrons. What's cool about this picture is the man who came up with the concept of the Van Allen belts is holding the device that proved their existence. Explorer 1 proved, or rather discovered, the existence of the Van Allen belt. So that was actually scientifically useful. In other words, it didn't just exist to send out radio signals until its battery died. It actually did some real science. But it also had a battery, which also died. So this satellite did not operate for very long. It had no means of powering itself. However, here's another American satellite. Let me get my head out of the way there. Oops. So that is Vanguard 1. And Vanguard 1 was the first solar-powered satellite. See, you can actually see the little solar panel there. You can also see how adorably tiny it is. Vanguard 1 was launched, what year was that? 1958. And what's pretty neat about Vanguard 1 is it is still up there. Vanguard 1 is the oldest human-made object orbiting our planet. So it's been up there since 1958. Of course, it's not operating anymore, but it's still up there. I think that's pretty neat. We'll talk a little bit more about that in a minute. Let me go back here a bit. Let me show you something else. This is the year 1966, and as you can see, there weren't that many countries that had the ability to either make or launch satellites. So the countries with the lines through them have space launching capability. The countries without lines did have satellites in 1966, but of course they made use of other countries' launch capabilities. So that was 1966. This was a few years after all those events of the late 50s. This was around the time that satellite science really started to explode. Countries around the world wanted in on the satellite game. Satellites were a big deal. So this graphic was actually generated in 2016, which was the 50th anniversary of a few notable missions. And now you can see in the year 2016, many, I don't know if I want to say most, but many countries either have satellites or have the capacity to launch them, or both. This is a big deal. This is one of the reasons I wanted to talk about satellites tonight. Is it's one of those technologies we've seemed to have forgotten about. It didn't take us long. It only took us half a century to begin taking them for granted. And it's funny because they're integral to our everyday life. Satellites are very important to us. Every one of us, for example, appreciates a good weather forecast. Well, weather satellites are obviously responsible for the increasing accuracy of our ability to predict the weather. And of course, something that we all make use of constantly now, GPS. And then if you're in other countries, there's other services like GPS, like GLONASS and BIDOU or BIDU and Galileo. These are all navigation services. It's a big deal. And then before those things became really popular, we had already begun to use satellites for things like telecommunications, relaying telephone signals, and then sending live TV. TV was actually a big driving force behind research and development into satellites, because suddenly it became possible to transmit over vast distance very quickly without having to use relay systems and long undersea cables, for example. On that subject, it's worth asking the question, why do satellites exist? Here's a picture of some cell phone towers here at the observatory during a lightning storm. I'm a big fan of lightning storms. I like to take pictures of lightning. And these cell phone towers, they're not rare, are they? You've all seen cell phone towers. They cover the planet. And they're tall for a reason, aren't they? The taller a tower is, the wider the area it can serve. The problem with towers, of course, is they are limited. You can build a tower, let's say 500 feet tall. There are actually some towers taller than that. But even a tower that tall has its limitations in terms of coverage. You might be able to cover, for example, a whole state or a handful of states, but you're not going to be able to cover, for example, an entire hemisphere. And let's not forget maintenance. If you have literally hundreds of thousands of towers all over the Earth's surface, those all have to be maintained. The ground that they stand on has to be rented, and people have to fix them up. They have to be powered and all these things. We figured this out a long time ago, that towers would be problematic. They have their pros and cons. One of the cons is a single cell phone tower is enormously cheaper than a satellite and its launch, but they're still a thing. What if you could have a tower that was 300 feet tall or 500 feet tall? What if you could have a tower that was 26,000 feet tall? Of course, that's ridiculous. But you could actually perhaps increase your footprint enough to service a huge number of people with a single device. What if you had a tower that was 26,000 miles tall? There are satellites that are that high. Satellites are attractive because they can provide coverage to huge areas, like I said, an entire hemisphere, without need for constructing thousands of towers. So that's one of the reasons satellites exist, because it gets you up high. Being high gives you the ability to see a lot of stuff. It allows you to service a lot of areas with different technologies, for example, telecommunications, like I said, relaying telephone or video or internet. There's also military surveillance opportunities. When you have a view of an entire hemisphere of a planet, it allows you to very safely spy on people if you wish, and there's plenty of military satellites that do exactly that. So I just gave you one example. Coverage. Coverage area is one of the reasons that that satellites exist. Another reason is much more scientific. It has to do with what we call atmospheric extinction. Earth's atmosphere absorbs many wavelengths that we are interested in studying. I have a lot to say about that, but before I do, I'm going to pause and I'm going to look for some questions. Let's see what we got. Oh, look, we have a young person here. Oh, well, what do satellites do? That's funny. I was just in the process of answering that question. So I just gave you one example, telecom. And now let's go into the science a little bit. You're going to learn that, indeed, militaries were often behind funding of satellite projects, but there is also a great deal of important science that can only be performed in outer space. Let me show you why. I'm going to show you a strange image. This chart illustrates atmospheric opacity. Now, let me explain what you're looking at here. This is the entire electromagnetic spectrum, starting from radio at the bottom, all the way up to gamma rays. This strange tan or brown material indicates atmospheric opacity. If this line is at 100%, that means that the atmosphere of Earth does not allow those wavelengths to penetrate at all. So, if you wish to study the universe in gamma ray wavelengths, or X-ray wavelengths, or even ultraviolet wavelengths, you can't do it on Earth's surface because the atmosphere absorbs those wavelengths. Now, you see this rainbow here. This is what we call the optical window. visual wavelengths, those that we can see, do penetrate Earth's atmosphere fairly well. As you can see, they don't make it all the way to the ground unscathed, but visible light does make it to the ground well enough that we can study it on the ground using telescopes. So, if you want to study the universe in visible light with your eyeballs or with a telescope attached to your eyeballs, you don't have to go to space. You can do it from the comfort of your backyard, for example. And of course, astronomers can do it from the top of a mountain. You want to do it on a mountain because the higher you are, the less air there is between you and outer space. Air is not your friend when it comes to astronomy. Then you see all these other random windows. These are infrared windows of various wavelengths. This one here goes down to about 40,000 feet. We can actually observe infrared wavelengths from aircraft using this particular window. So there is a famous 747 aircraft with a telescope in the back. It's an infrared telescope. Then we have infrared, which is blocked. And then we have a huge, I should say other lower energy wavelengths of infrared, which is blocked. And then we have this huge radio window. So we don't need to go to space for radio astronomy either. And then even then, there's still some wavelengths of radio that are also blocked. But this is one of the other reasons we go to space, because not all wavelengths penetrate the atmosphere. Now, this drawing here is of the Spitzer Space Telescope, which is an infrared space telescope. Here's Spitzer. This could not operate on Earth's surface because, again, those wavelengths are absorbed. Here's an extremely famous telescope, Hubble. Hubble is an ultraviolet and visible light telescope. It is pretty much obsolete in the visual spectrum. There are actually ground-based observatories that can now outdo Hubble, thanks to an amazing technology called adaptive optics. But Hubble's contribution in ultraviolet, again, could only be achieved thanks to its presence in outer space. And then here's another one. This is the Chandra X-ray Observatory, and this is something I'm going to talk about in a minute. This is a space observatory that observes the entire universe in X-ray wavelengths, and again, this could not be done on the Earth's surface. Now, I have more to say, but are there any questions about that, the concept of different wavelengths penetrating the atmosphere or not, and demanding space hardware to solve the problem? What do you think? There I am again. I'm going to go up here. There I am. Pretty soon I'm going to tease you. We're going to be looking at these satellites pretty quick. We're going to be talking about how they move, and that should be illuminating. So let's see, questions. Oh, that's a good question. How many satellites have been launched? Well, well over 4,000. As far as ones that are operational, it's about 1,400, although that number keeps increasing because of new missions. The thing about satellites, though, is they stay up there if they're high enough. So of the many thousands of things that have been launched in space, into space, many of them are still up there. We're going to talk about that right now. Hold that thought. Let's see who else we got. Oh, that's a good question. Who manages the number of satellites in orbit? So, this is actually kind of like real estate. Let me show you something. I'm gonna go to my satellite view here, and this is from Goldendale Observatory. Let me pause time. Now we're back to now. Okay, so this green line is the horizon. So everything below it is covered by the ground. See that? So you can't see it. If you look, I have all these satellite indicators turned on. These are all the known satellites and also pieces of large space junk. And you might notice that some of them appear to be in an arc. This blue line I just drew on the screen, let me turn off the other blue line so you're not confused. This blue line is the celestial equator, essentially a projection of our own equator into space. And you'll notice that these satellites seem to follow it. Those are equatorial satellites. We'll talk more about how they operate and what they do in a minute, but I want you to notice something. If I zoom in really close, there is spacing between them. They're not allowed to be essentially on top of each other. So, Intelsat, USA 107, that's a spy satellite. EchoStar, that's Dish Network. I don't know if any of you have Dish Network. DirecTV, that's a DirecTV TV satellite. Another DirecTV satellite. Their positions are regulated not because we're worried about them running into each other, but because we don't want the frequencies that they communicate to Earth with overlapping and causing interference or jamming. So various governing bodies around the world decide where you can put something, and you must get permission. You cannot just launch something into space willy-nilly and park it up there and say, oh, I'm just going to send signals. You'll be in huge trouble, and you will incur literally millions of dollars in fines if you do that. So in the United States, the FCC would be the governing body that regulates spectrum and also physical locations because of spectrum. It's a good topic. Most spacefaring nations, or I should say all spacefaring nations, are respectful of these rules because it affects them too. None of us want to get our satellites jammed so that we can't use them. They're very expensive. It's a good question. So hold that thought, because we're going to talk more about that. Now we're back to moving. I'm going to say a little more before I do that. I see another question. Oh, what about the Webb telescope? So the James Webb telescope is also an infrared telescope, and you will often hear it referred to as the spiritual successor of Hubble. That's only kind of true because Hubble is not an infrared telescope, but James Webb is, and it's a good question someone just asked because again, being infrared in nature, its study must take place in outer space. Okay, now I'm going to show you guys something rather cool. This is, hold on, try to bring it up. This is an accurate simulation. Oops, wrong button. This is an accurate simulation of every single thing orbiting Earth bigger than, let's say, a baseball. This is live and this is updated every 15 milliseconds. The red dots are active satellites, that is to say satellites that are actively working and doing something useful. The blue dots are rocket bodies, so those are delivery vehicles, so to speak. And the white dots, well, that's space junk, lots of debris, pieces of things. Those could be entire dead satellites or just pieces of dead satellites. All this stuff orbits our planet. Now, this is being updated in real time, so this is the real positions of things. You might notice a train of satellites. We're going to talk about that. Oh, look, Starlink. We'll talk about what that is in a minute. But if I zoom in really close, you can actually see these things moving. See that? Now, I'm going to show you, hopefully, a helpful and informative video. Okay, this animated chart depicts different orbital regimes. There are different, let's say, altitudes or places above Earth that are popular for different reasons. So some of these are very famous. You notice, for example, GPS up here, Galileo, Beidou, GLONASS. These are all navigational systems, and they orbit within what we call the medium orbit regime, also known as the circular orbit. They're high enough that they can actually maintain a mostly circular orbit. We'll talk about why that's more difficult at low Earth orbits in a second. So yeah, medium orbit, if you can see here the distance, it's over 10,000 miles above Earth's surface. It takes about average of 12 hours for these bodies to orbit our planet at this altitude. However, these are mostly not the satellites that you see. When you're looking up at the sky at night, the satellites you see are much closer, and those would be usually, and those are the low Earth orbit satellites. Now look as they whip around. It only takes them about 90 minutes to orbit our planet. This was true even of the early satellites like I mentioned Sputnik. Sputnik's orbital period was about 90 minutes, and that's because it was in low Earth orbit, also known as LEO. The majority of human space exploration, both with people like crews and robots, has taken place in low Earth orbit, mostly for reasons of cost. It's so difficult to get higher than that without spending huge amounts of money on, for example, fuel and the large spacecraft required to hold that fuel. Notice something orange there, the inner Van Allen belt. This is dangerous. The high radiation zone, the Van Allen belts, are actually destructive to the electronics and satellites, so we tend to stay under them, or if we can go, of course, over them. Now, let's address some nonsense on the internet. There is this absurd belief I've noticed floating around in like message boards and on YouTube, of course, that the Van Allen belts are some sort of impenetrable force fields that prevent escape, that we're trapped on our planet because of the intense doom radiation from the Van Allen belts. I just want to make it clear, this is ridiculous. It is incorrect. It is true that the Van Allen belts are dangerous. So what we do to avoid that danger is, like I said, either we stay below them or above them, or if we're forced to go through them, we do so quickly. Now, human beings have only ever left low Earth orbit once. And before I tell you, and some of you might already know where I'm going with this, consider that almost 100% of human space exploration, that is to say people, crews in spacecraft, has taken place only a few hundred miles above Earth's surface. So just 200, 300, 400, 500 miles above. There is only one set of missions that left, and that is, of course, the legendary Apollo program. But they weren't just trying to leave Earth, were they? They were going somewhere else. They went to the moon. So the Apollo astronauts and the various missions, and by the way, I'm not just talking about Apollo 11, I'm talking about all of the Apollo missions, including, for example, 10, where they went to the moon but they didn't land. Apollo 11, Apollo 12, even Apollo 13. That mission didn't go very well, but they still left low Earth orbit, 14, 15, and 16, 17. These missions are the only occasions in all of history where human beings left LEO, left low Earth orbit. Think about that. Everything else has taken place with people very low. I have more to say. I'm going to leave this on screen because I have more to talk about, but I know it's a very busy graphic and I'm going to keep explaining it, but let's see if there's any more questions. Oh, I see someone wrote Apollo missions. Very good. You got it right. So let's see. Questions. Oh, yeah. So someone wants to know how I found that cool live 3D view of our neighborhood in the sky, the robot zone above Earth. It has the best name. If you Google stuff in space, you can find that. And I'm going to be going back to that in a minute because I want to show you some cool stuff. Yeah, so stuff in space, if you Google that, it's pretty cool. Big fan, big fan. Now, I talked a little bit about low Earth orbit. I talked about medium orbit. And I haven't talked about this one, geostationary, also known as geosynchronous orbit. Notice something brilliant here. There is a satellite here depicted in geostationary orbit, and we have a sort of a laser beam connecting it to the Earth. And if you look at the Earth, you'll see that Earth spins, rotates, and you notice the laser beam seems to stay fixed on a single part of the Earth. That's because at this altitude, which is around 26,000 miles up, from the center of Earth, by the way, it's a little bit less than that if you read from the surface, but around 26,000 miles from the center of Earth, it takes you 24 hours to orbit our planet. By the way, I should probably go over the basic orbital mechanics here. It's kind of common sense once you learn a little bit about this stuff. The reason this can go slowly is because it's farther from Earth. Essentially, it experiences less gravitational attraction. These guys down here have to zip around super fast because they're very close to the Earth and they, of course, experience much stronger attraction. What would happen if they were to slow down? Well, of course, they would burn up in the atmosphere. Speaking of which, let's watch some exciting, violent videos. Watch this. So this is the Japanese Hayabusa spacecraft returning to Earth and being obliterated by Earth's atmosphere. And by the way, this is not a tragedy. This was expected. This is what happens. Let me turn off my head there. Look at that. Look at that amazing, glorious shower of sparks. Any of you who have ever been lucky enough to see re-entering space junk, it is quite a display because it's slow. Let me show you just how slow. So I'm going to go to the next video here. Now look, this is a cargo vehicle that had delivered cargo to the International Space Station. And it looks slow, doesn't it, compared to, for example, a shooting star. Meteors can be going over 100,000 miles per hour, where this is going only about 16,000 miles per hour. So it appears much slower. This is one way you can tell space junk apart, or any re-entering spacecraft, from meteors, because they're so slow. Suddenly that great velocity doesn't sound so impressive. Here's another cargo vehicle, delivered cargo to the International Space Station, and now it's burning up in the atmosphere. Again, very slowly, very impressive thing to see. These are actually home movies that people have put on YouTube. I would give credit if I knew who to give credit to, I promise. So I have seen space junk burning up, never anything this spectacular, and it is very noticeable how slow it is. Yeah. Let me get my head off there again. Cosmos, what was that number? I forget, but anyway, that's a Russian military satellite burning up in the atmosphere. Look at it. Notice how it's broken up into many, many pieces. The re-entry into the atmosphere is a violent event, especially if the satellite is out of control and tumbling. So it's being actively destroyed by the atmospheric friction. When you're going that fast, when you're going 16,000 miles per hour plus, oh, there's a nice explosion there, see that? Just hitting air is like hitting a brick wall. Think about that. This is another cargo vehicle being spectacularly destroyed. I'll tell you guys a pretty funny story. A few years ago here at the observatory, I was here in the middle of the night, and all of a sudden the phone starts ringing, and I was ignoring it at first, but it kept ringing, so I thought it had to be some emergency. And I pick up the phone, and this person is screaming, "Are you seeing this? Are you seeing this?" And I noticed it was a Montana phone number. So I immediately thought I'm probably not seeing it, whatever it is. And indeed, I didn't. I ran outside and I didn't see what this guy was talking about, which was essentially this. He was seeing some kind of, it turned out to be a Chinese rocket body that had re entered prematurely and was burning up over Montana. So that was quite impressive. And the way he described it, it was kind of like these golden sparks, kind of like you're seeing in these videos. Yeah. So, yeah, I wish I could have seen what this guy was yelling and screaming about, but I did not. But I would imagine it probably looked a lot like the video you're seeing in front of you right now, as far as how it appeared. And by the way, when they flash like that, when they explode, that can actually be materials like liquid fuels, for example, blowing up. This is one of the reasons why when satellites are deliberately deorbited, they are emptied of their fuel first so that they don't cause spectacular explosions and freak people out. Also, the fuel can be toxic. For example, hydrazine, which is a maneuvering fuel, is extremely toxic, and you don't want that landing on the ground. So having it burn up in the atmosphere is apparently okay. So I have more to say about this, but are there any questions so far? Let's see. The main sandwich. Okay, yeah, so someone pointed out the speed difference. So it's all about relative motion, isn't it? When something is stationary, you only say it's stationary because it shares our common inertial reference frame. If you say something is moving, it's because you have different frames of reference. By the way, on that subject, when we talk about these satellites going 16,000 miles per hour, that is, of course, in relation to a stationary surface target on Earth. When we say the space station is going that fast, again, that's based on Earth's reference frame. However, Earth is not standing still, is it? Earth is traveling around the sun at about 66,000 miles per hour, which makes the speed of these satellites seem very slow by comparison. And then our sun, and our entire solar system by proxy, is orbiting the core region of the Milky Way galaxy at an astonishing 514,000 miles per hour. So, yeah, these satellites are essentially standing still, depending on the context. And by the way, you have to draw the line somewhere when you are talking about velocity, because you'll go crazy trying to take account of all the different motion vectors at work. There is no such thing as stationary. Nothing is standing still. If you were to say something is floating around in space, they're really not doing that. There's going to be some motion involved. And it's something that's worth talking about as we discuss orbits. Now, I mentioned that these fireballs you're watching were all intentional. These were not like tragedies. These were not mistakes. These were not accidents. These were vehicles that were intended to be destroyed upon re-entry. It is irresponsible to leave things in space, allowing it to become space junk, and it is best practice to destroy things deliberately so they don't hang around up there presenting a hazard to other objects, other bodies, other vehicles, other missions, even people. We don't want any people to be injured because of space junk impacts, for example. That being said, it's important to understand that this will happen whether we like it or not. Mother Nature takes care of it for us, so to speak. Low Earth orbit satellites are very short-lived. Once they run out of fuel, they can no longer maintain their positions. They can no longer resist drag. We'll hold that thought. We'll talk about that. And gravity anomalies. So listen to this. You don't normally hear the word drag associated with space because you know, of course, that space is empty. It's a vacuum. We don't expect for drag to be an issue. But low Earth orbit is so very low, like I said, only a few hundred miles up, that there's a little air, just a little bit. And that tiny amount of air does present appreciable drag to an object going tens of thousands of miles per hour. And it will rob them of velocity gently, gradually, over time, until the orbit of the object decays. Again, assuming you haven't boosted its orbit by adding energy somehow. I'm going to bring up a picture of the International Space Station really quick. This is kind of a neat story. Even though we're talking about satellites, I want to make it clear this is not a satellite. But notice the giant solar panels on the space station. And then these white things, these are space radiators to keep them cool. Space is not cold. We'll talk about that in another video. These solar panels and these radiators do create some drag. They're not even 300 miles up. And sometimes the space station will actually deliberately use the solar panels as a sort of air brake if they need to reduce their altitude. And by the way, the reason they might want to reduce their altitude is kind of scary, and it has to do with what we're talking about tonight, which is space junk. To avoid collisions, they will sometimes deliberately reduce their altitude to literally dodge debris, which is always being tracked via radar. Again, it's very clever. They can actually use the solar panels as air brakes to slow them down. But then you might, well, then how do they speed back up? The space station does have its own thrusters and its own fuel. However, they don't use it because it's expensive and kind of an emergency contingency to have it. So they actually will utilize the fuel of any given docked spacecraft. Very clever. They essentially act like tugboats to speed them up if they want to go up. So if the space station needs to increase its speed and thus increase its altitude, they will fire the thrusters of docked spacecraft. Very, very clever. Okay, so I mentioned drag. That's one of the reasons that low Earth orbit satellites tend to return quickly. I mentioned that Sputnik only took about 3 months. But I'm going to show you another thing you might not be aware of. This is kind of neat. Check this out. This weird spinning blob is clearly a globe of Earth, but you might notice that it's lumpy. I'm going to pause this. Oh, okay, fine. I paused it on our hemisphere. How convenient. This lumpy sphere illustrates gravity anomalies. Earth's mass is not uniformly distributed across its surface and within. And we discovered this using satellites way back in the late 50s and early 60s. We discovered that their orbits were decaying faster than expected, and it's because Earth's gravity is not uniform. Notice that the mass anomalies, the gravity anomalies, correspond to known geographic features. For example, here's the famous Yellowstone supervolcano that's going to kill us all, hopefully in distant future times. Notice we have a mountain range here. Not surprising that a mountain range would have a high mass concentration, more gravity. Let's go over to Hawaii here. You see the volcanic range that gives birth to the Hawaiian Islands. Over here we have the famous Ring of Fire in Asia. This is an enormous subsurface volcanic range, and again, mass concentration. But these mass concentrations are not always volcanic in nature. For example, here's the Himalayas. The Himalayas are not the result of just simple volcanism, but of continental drift. Literally, the Indian subcontinent is being shoved up into Asia, and it creates this compaction of Earth's crust. And so we have this, again, mass concentration. But notice below India, we see a reduction in density because the material is being kind of spread apart by continental drift, like I said. Very interesting. More mountain ranges all over the planet. Interesting. Earth's, I'm going to slow this down. It looks a little annoying. There we go. That's better. Earth's gravity is not homogenized, and so you have to take this into account when you're trying to orbit Earth closely. Now, this effect is less pronounced the farther you get away from the planet. Essentially, the anomalies average out. So that's why I mentioned earlier that medium orbit can provide a more circular orbit and be maintained more easily because you have less of this gravity anomaly to worry about. Also, there's no air at all, so there's no drag whatsoever. I don't want to, at the risk of repeating myself, objects that are very low in orbit can only stay up for a few months or years, but objects that are in medium or high orbit can stay up for centuries, millennia, even eons, because there's nothing that will cause them to slow down enough to crash into the Earth. I have a lot more to say, but are there any questions so far? I see a lot of questions. What is space junk? Yeah. Oh, junkyard orbit. These two questions are very complementary. So someone asked about space junk and also what a graveyard or junkyard orbit is. Let me go back to my orbital regime chart here. Notice we have up here graveyard orbit, and notice it's 300 kilometers higher than the geostationary orbit. It's very simple. I mentioned earlier that it's best practice to deorbit deliberately used up hardware so that it does not become space junk. This is not always a realistic prospect because, for example, in the case of geostationary satellites, they're so high up that it would take a significant amount of fuel for them to slow down enough to crash back into the planet. And as we mentioned earlier, adding lots of fuel to a satellite is a big problem because the fuel has mass, et cetera, it costs, blah, blah, blah. So sometimes, depending on the situation, it's acceptable to, instead of destroying a satellite via deorbiting, boosting it into an orbit that is not going to be used for anything. That's what a graveyard orbit is. Graveyard orbits are a much cheaper alternative than, sometimes, again, depending on the situation, than adding the fuel necessary for a satellite to be deliberately deorbited. Now, someone asked essentially what is space junk, and like I said earlier, it could be entire dead satellites, or it can be broken pieces of things, not just satellites, but also the rocket bodies that deliver them. It's important to note that the velocity that allows the satellites to stay in orbit is provided by those rocket bodies, and they're not slowing down either. So the rocket bodies will often stay up there just like their payloads will. Any questions about that? Let's see. Oh, how much time? Oh, that's actually a very good question. So, how much time does it take to make a satellite? It depends. So some satellites, especially science satellites, research satellites, can take decades to build. The Hubble Space Telescope was planned way back in the late 70s, and it didn't launch till the 90s. That's an extreme case. James Webb is a good example. It's taking forever to be launched. But then we have satellites that can be mass-produced, the famous Iridium satellites, for example. Notice Iridium are actually mentioned on here. Yes, they are. The Iridium satellites are also low Earth orbit, and they were, past tense, used to provide a global telephone network. And they made history by being one of the first mass-producible satellites. They could be built multiple per month, kind of like a car assembly line. They could be built for the cost of millions of dollars as opposed to hundreds of millions or billions. By the way, millions of dollars may not sound cheap, but that's kind of a bargain when it comes to satellites. And they were launched in great numbers. And again, the great numbers were intended to provide global coverage. Iridium pioneered this concept, but there are other firms doing the same thing, and doing it with gusto, I might add. One thing I want to mention before we're done tonight is the SpaceX Starlink system, which is all of those things I just mentioned turned up to 11, because the Starlinks can be produced extremely quickly at extremely low cost in extremely big numbers. And we expect to see literally thousands of just Starlink satellites orbiting the Earth over the next 10 years. So yeah, interesting question. Now, when it comes to manufacture, people assume that satellites have to be expensive, that they have to be essentially the playthings of big governments and research firms and companies. But in fact, there is something cool. I don't know if any of you have ever heard of a CubeSat. So this is a CubeSat. Notice it's extremely tiny. Notice that its antenna is actually a piece of tape measure that someone has cut. CubeSats can be built using literally off-the-shelf components or improvised components in the case of that tape measure. And this is something that a regular person could afford to do. In fact, high schools have built cube satellites. Now here's the best part. I've talked about how it's very expensive to launch things into space because of mass. Because CubeSats are tiny and lightweight, they're relatively inexpensive to launch. Now I say relatively. It's important to remember that the going rate for years to launch something into space was about $10,000 a pound. Thanks to Starlink and other innovators, it has dropped down to about half that, but it's still not exactly cheap. So it's not free to put a cube satellite into space, but it is affordable. And these satellites can be built by anyone who's interested in doing, for example, Earth science or ham radio operators. There's actually some ham sats they're called you can contact with a shortwave radio. And again, these are made by regular folks, probably pretty nerdy folks with some hopefully generous friends who can afford to pay for the rocket fuel, but still regular folks. Here's 3 of them being launched at once. So they can be launched in swarms like that, and sometimes there have actually been dozens of these launched in a single orbit before. So that's kind of neat. And I mentioned the do-it-yourself aspect. Check it out. So you can go on the internet and buy the parts for these things. Questions about that? I want to go over propulsion really quick. Here's a picture of Deep Space One, which was an important probe that had a unique, this is a drawing of course, had a unique propulsion system. Before I talk about that though, let's see about questions. Okay, so I'm going to keep going then. So everyone knows about rockets. Everyone knows about rocket engines. Satellites don't tend to have rocket engines. One of the most common questions I receive at this observatory, when people learn about the great speed of things, when they learn, for example, let's go back to that space station picture. When they learn the space station is going almost 17,000 miles per hour, or Iridium satellites, here's one of those Iridium satellites, again, going over almost 17,000 miles per hour. People say, well, how does it go so fast? How does it propel itself? My goodness, it must have huge gas tanks if it can, burn at such speed for so long. This came up a lot during the New Horizons mission. When we went to Pluto, it took us 9 years to get there, around 30,000 miles per hour. And people said, wow, a machine that can go 30,000 miles per hour for almost a decade, it must be a giant fuel tank. Wrong. It's very important to understand that when it comes to almost all spacecraft of all types, for the majority of their mission, they are coasting. The satellites in this case have inherited their great velocity from the rocket which delivered them into space. They are not propelling themselves, they are coasting after being lobbed into orbit by huge rockets full of fuel. Most satellites do not have the ability to dramatically alter their course. Most satellites cannot change their vector substantially, they cannot change their altitude substantially. And if they can, they have to do so very gently and gradually over time because they're not going to have big, powerful rockets that have to have fuel and oxidizer, two things that require tanks and weight, etc., etc. So that picture I just showed you there, this is Deep Space One, which was one of the first spacecraft to use an ion drive. Ion drives are real. I know it sounds like science fiction. This is a real picture of an ion drive. In fact, they are science fiction because they're mentioned in multiple science fiction like Star Trek and Star Wars, but they do exist. Instead of using a heavy rocket fuel, ion drives use high voltage electricity to ionize, hence the name, a very low weight gas, like in this case, xenon. And xenon gas can be compressed enormously into a small tank. And again, it's very lightweight and can then be accelerated to enormous velocities with high voltage. So this stream of plasma you see emanating from the back of this device is actually a stream of ionized xenon atoms. And the thing that's amazing about this is essentially it's an electric propulsion system for space. Even though it is using a fuel in the form of xenon, it is mostly powered by the sun because this is a solar-powered, in this case, spacecraft. You saw the solar panels on the Deep Space One image. So essentially, if it has sun, it has power to run. It will eventually exhaust its xenon supply, but that takes a very long time because you can, again, pack a lot of it on you. So that's one of the ways satellites can maneuver ion drives. However, there's no free lunch. Whenever you come up with some clever solution to a problem, it often presents new problems. And in this case, the force that an ion drive produces is extremely minimal. It's been compared to a piece of paper resting on your hand. You're thinking, well, you can't do any useful work with a piece of paper resting on your hand. It's true, on Earth you can't. Gravity, friction, air, whatever, that much thrust is not going to do anything useful. But in outer space, with the lack of friction, you can, believe it or not, propel something with the force of a piece of paper resting on your hand. But it takes time. So it might take literally months and months for one of these satellites that use this technology to appreciably change its position. Now, here's a really cool device. This is one of my favorite inventions. This is called a magnetorquer. Magnetorquers are incredibly clever, and when I first learned of their existence, I thought, wow, human beings are so clever. Some of you might recognize this as simply two inductors. Inductors are simply coils of wire, and most of you probably know from grade school, when you pass electricity through a coil of wire, it produces a magnetic field. Now you're thinking, well, what good is the magnetic field? Well, the magnetic field interacts with Earth's magnetic field, allowing the satellite to either be attracted or repelled by the geomagnetic field. And again, slowly, subtly, over time, a magnetorquer can alter the position or trajectory slightly, or the attitude of a satellite. And again, without the need for fuel at all. In this case, no fuel required, simply electricity. Very clever. Back to that CubeSat picture, you might even notice something. If I zoom in here, you'll see a magnetorquer right there inside of this guy's homemade satellite. Imagine that. Cool. Brilliant. In this case, you'd use it mostly for orientation, so you could point the satellite where you wish. Again, without the use of any fuel at all. Aren't we clever? Questions about that? I think that's an interesting one. Questions. I have a few more things to show you, including some really cool stuff. How much will observational astronomy be affected by Starlink? So let me show you a video. I get asked this question a lot about whether or not Starlink is bad for astronomy. Check this out. So this is at the observatory. And what was that? It looks like laser blast going on. Do you see that? Let me play that again. I'm going to play it in slow motion. Hold that it's dawn now. Here comes the sun. Oh no, ruining everything. That's what really ruins astronomy, the sun. So I'm going to slow it down. Oh, see the satellites zooming by, the Starlink satellites? Those are Starlink. Okay, so much has been said about the possible impact of Starlink on ground-based astronomy. And this is an opinion, I'm not speaking for state parks or anyone else, just my opinion. I feel that the issue is somewhat overblown because it doesn't make it impossible to do astronomy. It simply makes it less convenient because it requires astronomers to either reduce or eliminate these, I'm trying to find a good spot, yeah, eliminate these bursts of light from Starlink from their data or conduct observations only when Starlink is not going overhead. The reason I feel that it's a worthwhile compromise is because Starlink is trying to provide 100% global internet coverage. And if you want to disseminate knowledge, including astronomical knowledge, it's important that we get everybody on the internet. And a lot of countries are not. Essentially, fast internet is something that only rich nations have access to. And with Starlink, theoretically, the entire planet could have access. Speaking of which, let me show you something. Here's a launch of Starlink. Let me go ahead a little bit. I want to show you how they launch these things. So here is a launch, of course. And let me go back a little bit more. This fairing up here on this rocket contains over 60 satellites, 60 Starlink satellites. They launch them at 60 at a time. When it goes up into space, the rocket will spin. Let me show you how that works. Watch this. And the centrifugal force created by the spinning actually causes all of the Starlink satellites to be deployed. Here they go, watch. Maybe I should speed it up a little bit. There we go, I did. Keep waiting for SpaceX to launch their satellites. There's the beautiful, there it goes, there they go, all 60 satellites at once, launched in a big cluster. Now, people have seen this from the ground. I've taken pictures of it before. Here's a picture of a Starlink swarm a few hours after launch. This was the second go-around. It only takes them 90 minutes, and I saw it the first time, and it was an astonishing thing. There was in a big clump, and so it looked like this huge wall of light going across the sky. And by the next orbit, they had stretched out like this. By the next orbit, they looked like this. Let me turn off my head there. If you zoom in here, you can see there is a separation between them now. So over weeks and months, they will separate. Now, this is important because some of the complaints about Starlink originated immediately after launch when they were in a huge bright clump. But over time, they break up into a much wider constellation and also at a much higher altitude. And as a result, they're less disruptive to astronomy. Also, they've experimented with coatings on the satellites which are less reflective and makes them, again, less disruptive. I want to make it clear, the problem has not been solved. It has been somewhat mitigated. We will see. We will see how this ultimately affects ground-based astronomy. It may force us to do more space-based astronomy in the future. Now, we're almost out of time. I want to go back to that live view of the entire sky. And I want to show you a few things. So let's zoom out here a little bit. Loading Earth and all the satellites. And if you look, you can see this string here. This is a train of Starlink satellites, recently launched. And here's another one, recently launched. In fact, that one over there is the one you just saw saw a video of being launched. So as you can see, this one is younger, so to speak. This one up more recently, so they're more tightly packed. This one's been up there longer, and they're not as tightly packed. Here's another one. See this string? Theoretically, they will one day provide global internet coverage. It's already possible to sign up for beta testing if you're interested. Now, in the short time I have left, I want to show you a few things. Notice the geosynchronous orbit, the 26,000 mile high satellites that appear to orbit in only 24 hours, and I guess they really do. They don't appear to, they really do. But it causes them to appear to remain stationary. Notice this medium orbit, this kind of cloud around the Earth, and then you get close again, and you got the low orbit. Now watch this. I'm going to type in some famous things. Navstar is the GPS satellites, and as you can see, medium orbit. Notice how they surround Earth in sort of like a ball of yarn. Again, medium orbit, not low Earth orbit. GLONASS. GLONASS is the Russian equivalent of GPS. As you can see, it's not finished yet, but it is a similar orbit. Beidou is a Chinese system that is actually a hybrid. It has both high and low orbit satellite, or rather medium orbit satellites. But now let's take a little history detour here really quick. I'm going to show you something. Random different satellites have different orbits, as you can see. Here's something. Debris, what's this? Cosmos debris, so that's a broken Russian spy satellite. Look at that. Hold that thought. I'm trying to find one in particular that had a very interesting orbit. If I don't find it quickly, I will go on to the next thing. Oh, I think I found it. No, that's not it. Oh, here it is. It's a rocket body from an American launch. Let me just type it in for you. I'm going to type in Vanguard. And notice, Vanguard 1, there it is, launched in the year 1958, still orbiting Earth. But, interestingly, the rocket body that delivered it, debris here, rocket body Vanguard, also orbiting Earth. So not only is Vanguard 1 the oldest, let's say, satellite orbiting Earth, the stuff that helped to get into space is also up there still after all these years. Vanguard 1 will eventually re-enter in something like, let me think, I wrote it down here, 240 years. So it's expected that Vanguard will finally burn up in the atmosphere in about 240 years. So oldest thing in space. Now, one last thing I want to show you really quick on this topic. Notice this huge orbit. Let's see, I'm going to type in, let's see. Notice this really bizarrely eccentric orbit here. See this dot here? CXO, that is the Chandra X-ray Observatory. It's interesting that its orbit is the way that it is because of its mission. Because it's an X-ray observatory, it has to get far beyond those disruptive Van Allen belts that we talked about. And it only performs its science when it's far away. However, when it's close to Earth, like here, that's when it dumps its data because it has a higher bandwidth. So it'll do its science observations far from Earth out here when it's away from Earth's disruptive Van Allen belts. It's important X-ray astronomy, and then it dumps its data back to Earth when it's close to our planet. Isn't that clever? That's an example of why we have different orbital regimes for different missions. One last thing. Notice the orbits in general here. I'm going to refresh this. You might notice that the Clark belt, which is named after Arthur C. Clarke, the geosynchronous belt here, has some crookedness to it. There's a reason for that. So you see lots of active satellites in the geosynchronous belt, but then we see some space junk, and then we see, like I said, that it's kind of crooked. Notice this? It is crooked for a very interesting reason. A natural body is responsible for the crookedness. What natural body do you think I'm talking about? Let's see if it's in the chat. What natural body could have pulled those satellites off of their original orbit? What do you think? The moon. Very good. Check it out. So, as you can see, the moon's orbit, its orbital plane, does not agree with Earth's equatorial plane. And as you know, as I pointed out, the satellites in the Clark belt orbit above Earth's equator. The moon does not. The moon disagrees not only with the obliquity of Earth, but also the obliquity of the entire solar system. So because everything's crooked, the moon is either going to be pulling them up when it's above our plane like this, or it'll be pulling them down when it's below the plane. But so you're thinking, well, why don't they correct for it? They do. Those satellites will correct for the perturbations of the moon until they run out of fuel. So the satellites can only remain parked, so to speak, in their proper geosynchronous positions as long as they have fuel to make corrections. Once they run out of fuel, the moon has its way and it tugs them up or down. I think that's very interesting. The funny thing is some of the satellites can continue to operate even though they are no longer in their exact positions. It all depends on how precise the beam has to be, the transmission signal beam, or what their mission is. If they're TV satellites, it becomes a problem because you have to go out and adjust your dish to adjust for this deflection, and that's not going to work. So depending on what the mission of the satellite is, you may or may not be able to keep using it. Thanks to good old moon pulling everything out of whack. This is why we can't have nice things. Mother Nature's always foiling our well-organized technology, isn't she? So, I'm going to start wrapping it up, or actually I am wrapping it up. Let's see if we have any questions. Here's a picture of something. This is an iridium flare. I mentioned the iridium satellites. Those aren't happening anymore. I hope you've all gotten to see an iridium flare, because as progress marches forward, the iridium telephone satellites have been deorbited. That happened over the last 4 years or so. So the famous iridium flares, where the sun would bounce just right off of the satellite's antenna, these don't happen anymore because most of those satellites have been removed. So I was happy to get this picture. I didn't know. It's kind of dramatic for me. I did not know this would be the last time I ever saw a bright iridium satellite. So I was happy to take this picture. And that was in July of 2017 I took that picture. Yeah. All right. In the interest of wrapping it up, looking at questions. Let's see. Can you talk about solar sails? What is this? Yeah, so the solar sails is a means of propulsion that uses an enormous, I don't have a picture handy, but an enormous surface area, very lightweight sail to, believe it or not, receive thrust from either solar radiation or perhaps even a huge laser that we could build in space powered by the sun. Solar sail propulsion may be the future. But again, if you're trying to push something with a sail that's pushed by light, you need to make sure that the device you're pushing is a very low weight, very low mass. Yeah. Okay, so we'll stop at 8:10, so I have 4 minutes. So let's do 4 minutes of questions and answers. What do you guys think? Let me know. Blow up the chat. We love questions. Let's see. I'm watching the chat. Here's something fun while I'm waiting. So back to my view of the sky here. And again, please ask questions while I'm doing this. Look at all those satellites. I'm going to zoom in here a bit. Notice the geosynchronous satellites, but if I speed up time a lot, notice some of them are wandering around. Morelos 3, for example, seems to be a little bit off. See how it's kind of wandering up a little bit? Let's see if we can find some other broken ones. Oh yeah, look at that. These satellites are misbehaving, and the reason they're misbehaving is because they're out of fuel and can no longer affect significant changes to their attitude. Here's another one. This is an American spy satellite. That one actually I think is intended to move in the way that it does. Not all satellites are, like I said, intended to stay put, so to speak. I'm going to slow it down again. Did you see that Starlink train that just flew by? Let me go back there a little bit. See that? Yeah, so look at that. Look at that train of satellites there, guys. Those are all Starlink satellites. All right, let's see. Oh, that's a wonderful question. How common are collisions between satellites? In the graveyard, not common at all, because in the graveyard they're all spread apart. However, unfortunately, there have been some embarrassing collisions. For example, an Iridium satellite collided with a Russian military satellite a few years ago. The collisions are very bad because it's not like in a science fiction movie where there's a puff of fire and then the two objects cease to exist. When you blow something up in outer space, it no longer may appear to be an object, but now it's actually a debris field, and that debris field is still moving at the same speed. So you might have now, instead of a single object, a cloud of debris going 17,000 miles per hour. This is actually a good way to end the show. How do you deal with space junk? There's a lot of questions about this. And one idea is you could actually fire a net to lasso the larger things from a spacecraft. It's already been tested, believe it or not. There's also an idea involving lasers, where we use lasers to shoot down the small things. We're not vaporizing them like in a space movie. We're actually knocking them off course so they burn up in the atmosphere more quickly. Using, again, a laser to slow things down. When it's a small object, like a piece of something, you can actually slow it down with lasers. The idea is maybe you could have robots in orbit that are just constantly shooting down space junk. It's kind of exciting. Yeah. So let's see, on that subject. Well, you still got 2 minutes to ask questions, or 1 minute. Keep asking questions. Thanks for making this info. Hey, so thanks for watching, everybody. Are there any shards of the Apollo mission? Yes, some of the Apollo booster stages are still orbiting either the Earth or the Sun. You may have heard about the Snoopy module, which was I believe the Apollo 10 module, which was recently found, and it is orbiting the Sun. So it escaped our planet and is orbiting the Sun. It will do so forever, essentially, millions of years. Hopefully, maybe someday we'll turn it into some kind of orbiting museum, right? I do think about that a lot, that future humans might visit our space junk and, make it a tourist attraction for people to come observe. Look what these primitive people did. Look at this. Look at this artificial. Look at this. Look at this obsolete robot. How pathetic. You may have heard some of the old satellites from the 60s have been found by amateur astronomers and amateur radio operators, and actually have been woken up and talked to. Imagine that, a 50-year-old satellite that's still operational. I think that's pretty cool. Yeah. So, I guess we're about to, yes, solar flares have destroyed satellites. Back in 1989, there was a very famous solar flare. Let me show you a picture really quick that destroyed multiple satellites. Now notice this. This is a chart of solar irradiance, and notice that there was a spike back in the year 1989. There was an unusually active solar cycle, and a big solar flare destroyed multiple satellites and caused power outages in the northeast United States and in Canada by destroying transformers on the grid system. So yeah, solar flares can affect not only space hardware, but also ground-based hardware as well, because of Earth's own magnetic field being disrupted by the high-energy particle flux from the sun. Speaking of which, there's an image of the sun, and this is solar wind. This is the high-energy particles leaving the sun and distorting Earth's magnetic field into what we call the magnetotail. When this moves around violently, it can induce voltages on electronics and destroy, like I said, satellites, or high voltages on power lines, causing destruction of transformers. Yeah. Again, notice the shape. Earth's magnetic field is not symmetrical as you often see it depicted. It's being actively distorted by solar wind. And of course, there is no wind in space. Solar wind is the term we use for this endless barrage of high-energy particles and radiation from the sun. This is, by the way, also the reason for the Van Allen belts. These magnetic fields trap these particles and create those dangerous radiation zones we talked about earlier. Good questions. I was hoping you guys would ask more of these questions sooner, but it's fine. We got it. So. All right, wrapping it up. Let's see. By the way, I have to tell you, I don't want to be rude. I could do this for another hour, but I said an hour, so I want to be nice to the people who have limited attention spans and need to get out of here. So with that, I'm gonna start to sign off. Oh, so you know what? People are asking all these good follow-ups. Earth's magnetic field is crooked, and that's the reason for the South Atlantic anomaly. Some of you might not be aware there's a region above the South Atlantic Ocean with unusually high radiation. It's because of Earth's magnetic field being crooked and directing high-energy particles towards that region. Aircraft pilots who fly commercial routes in that region actually have to get radiation certification to work that route. And when you're a certified radiation worker, that means you can only do it for so many years before you reach an exposure limit, and you have to retire from that route. So that's an interesting thing. That's a very pertinent question. Thank you. So, well, my friends, I hope this is fun. I hope we learned a few things. That was the objective. It's not just edutainment. The edu is important. The edu, the education side of it. So we hope you learned a few things. This is, I would like to say with some certainty, not our last show on YouTube Live. Our next show will be about Earth's moon, and we'll be trying to do a live view of the moon from our big famous telescope. That may or may not be impacted by weather. We will see. It has been cloudy and rainy lately, but who knows? We might get lucky. So yeah, we might get to see Earth's moon via the internet next Sunday. We're going to try to do these every Sunday night at 7 p.m. until something changes. Also, this on the docket is after the moon thing, we're going to talk about the three-dimensional nature of the universe and the distance and perspective of things, and also talk about whether or not space is actually cold. I mentioned that earlier. Space is not technically cold. And it's not technically hot either. It depends on your point of view. We'll talk about that in great depth during one of our future videos. All right, so cracking my fingers here, cracking my knuckles rather. I'm wrapping it up. The logo's about to appear on the screen. I hope you enjoyed your experience. And oh, I forgot. I have to do the YouTube thing now. Like and subscribe. We would love it if you would do both of those things. Unless, of course, you don't feel compelled to do so. We want you to be honest in your liking and subscribing. We want to make sure we provide positive quality content for the liking and subscribing too. All right, my friends. Have a wonderful evening. I'm signing off. This has been Troy Carpenter at Goldendale Observatory State Park.